Hi, and welcome to another geometry gem. In this gem, what we're going to do is we're going to find what the coordinates of a point that we know where it is in world coordinates. We're going to find what the coordinates of that point could be in some other local coordinate system that is not the world. So, for example, in this view, what you can see is that I have this point here, and I know that this point is in this XYZ world coordinates. But what I would like to know is for this other coordinate system that I have somewhere in three-dimensional space with some random location and some random position, and some random orientation, I would like to know what the coordinates of this point are in reference to this local coordinate system. You can see that the coordinate system is much closer, so they're going to be smaller. So what we've done here is we have written an algorithm to figure out that translation between the world coordinate systems of this point, the world coordinates of this point, and the local coordinates of this point in this other plane. This is an interesting application because we're going to see one of the advantages of using the dot product for projecting vectors on top of each other, which is going to give us a really interesting result. And it's also really good for operations of changes of basis. So understanding how to move from one coordinate system to another, and which will also be very useful for operations such as translations or reorientations from one coordinate system to another local coordinate system, which we will expand further in the next geometry gem after this one. So let me explain to you before the concept behind what we're going to be doing, and then I will get into the implementation of how we did this exercise. Let's draw some sketches, shall we? Okay, let's start by the beginning and let's start describing the actual problem that we're trying to tackle with this gem. The idea is that when we work with three-dimensional geometry, and we're going to work with the simplest kind in this exercise, which is a point in three-dimensional space, we have some sort of global coordinate system that we typically refer to as the world, which is the base of the coordinate system that we use to define every geometry that we have in our environment, right? So for example, this point may have whatever XYZ coordinates in the world coordinates. And typically what we do is that what we do is like to know what the actual XYZ coordinates in world coordinates are. What we do is we measure in each direction how far off that point is in units, in the whatever units we're using, and we measure that length along each one of the x, the y, and the z axis, and then what we get is the value for its x coordinates, its y coordinates, and the z coordinates. That's typically how we work in world coordinates, and it's something that we are very used to and we actually kind of get for granted right now, right? Okay. However, what the problem that I want to describe here is slightly different because very often, depending on what we're doing, we may actually have local coordinate systems or other coordinate systems that are not the world and that for some reason, we want to refer things to. This is very common, for example, in robotics, or this is very common when we're modeling in Rhino and we choose like a different C-plane to be working on, right? That's basically what we're doing is we're defining local coordinate systems that are somewhere else, and we want our numbers and our coordinates to refer to that coordinate system. So let's imagine we have a coordinate system in somewhere in the world, and the way to define this coordinate system will probably be something like defining where the center, the origin of that local coordinate system is, and which direction the three main axes, x, y, z, for that local coordinate system are. All right? If that's the case, then I may actually want to find this point which has global XYZ coordinates. What are the actual coordinates of that point in reference to that local coordinate system that we're working with? So in this drawing that I have, like very qualitatively, I could see that the XYZ coordinates of the point in world coordinates are probably going to be very large because it's fairly away from the center. But in these local coordinate systems are going to be much smaller number because it looks like the coordinate system that is very close to the point, right? Now, how would I actually find those values? Well, we would actually do the same operation that we do mentally when we work in world coordinates, we would pretty much do it with this local coordinate system. What we would do is something like, we would figure out in the direction of the main three vectors of that coordinate system, we will find out how far along each one of those directions this point is, and then measuring each one of those directions, we would get the x, y, z coordinates of that point in that local coordinate system. All right. So this point will basically have two sets of coordinate systems. One is two sets of coordinates. One is the coordinates measured in world coordinates, and the other one would be the coordinates measured in this other reference or local coordinate system that we're trying to describe. Okay, but how do I actually find the coordinates of this point here in regards to this coordinate system that we have here? How do I do that numerically? Well, we actually can take advantage of a very nice property of the dot product, which is that the dot product turns out to be the projection of one vector on top of another vector. Let me show you what that looks like. Okay, let's imagine we are zooming into the local coordinate system. We're just only looking at the coordinate system, at the local coordinate system, right? So we have this reference local coordinate system that is somewhere in three-dimensional space. And then we have the point that we want to find the coordinates in that reference frame. What we can do is we can create a vector that goes from the origin of that reference point to the reference point itself. Okay, so this is very easy to do because we know where this point is in world coordinates, and we also know where the origin of this reference system is in world coordinates. The next thing that we can do is we can project the vector, the position vector of this point in the local coordinate system, we can project it onto the x-axis of the local coordinate system. As we do that projection, we can measure in three-dimensional space how long that projection is, and then that will become the local x-coordinate of this point in this reference frame. Similarly, we can do the same operation for the y. We can project the position vector onto the y axis of the local coordinate system, measure that projection, and then that's the local y coordinate. And similarly, we can also do the same for the z direction. But now, how can we project a vector onto another vector, and how can we measure that distance? Well, it turns out that I think we have seen this in a previous gem, but we can take advantage of the dot product of two vectors, because it turns out that the dot product, one of the meanings that the dot product of two vectors has is that the dot product of one vector on top of another vector, so for example the dot product of vector A on top of vector B, turns out to be equal to the length of that projection all right, let me say this again. The length of the projection of one vector on top of another, that length equals to the dot product of the two vectors divided by the length of the vector that we are projecting on. And it turns out that if the length of B equals 1, then it turns out that the length equals just the simple dot product of the two vectors. And typically what happens is that when we have a reference system, typically the axis, the vectors that we use to represent the x, the y, and the z directions, those vectors are typically unitized, because that's what most reference systems, that's how most of them work. And actually, if they're not, if they're like 2 units long or 3 units long, it means that the system is actually scaled in one direction, and we would still get that effect of that scaling in the okay, I am writing on top of myself. So if we perform the dot product of the position vector times the one of the axis, we actually get directly the length of that projection on top of that axis, because we're going to be working on the assumption that the vector of the axis vector that we're going to be working on is a vector that is unitized. All right. So that's going to be very simple. What we're going to do in this gem then is going to be we're going to create a local frame. We're going to create a position vector from that frame into that point. We're going to project that vector on top of the 3 axes, and that's how we're going to find the 3 coordinates of that point in regards to that local coordinate system. You want to take a look at how that is done? It depends on the system that you're using. It depends on the framework that you're using. You will have to choose a form of representing this 3-dimensional coordinate system. In most computational environments, computational geometry environments, that would be typically represented as a 4x4 matrix with 3 vectors representing the x, y, z directions and another vector representing the position. We're going to be implementing this in Grasshopper with C#. So in Grasshopper incorporates a structure called the plane. And the plane is basically an object that also has 3 orthonormal vectors, x, y, z, and it has a location, it has an origin, which is basically the same thing as a 4x4 matrix at the end of the day. So this is what we're going to be using in this exercise. So let's take a look at that and let's get hands-on. Let's start. So what I have created here is, first of all, I have drawn a 3D point in Rhino that I'm bringing into Grasshopper. And you can see that if I deconstruct this point, I can see that the world coordinates of this point are 0.8, 5.6, and 3.9, something like that, right? And what I've also done is in order to have some other local reference frame, what I have done is I have created a plane by just using 3 points that I have also generated in Rhino, right? I have brought them into Grasshopper and I have created a plane oriented with these 3 points. Therefore, taking the first point as the center, the second point as the direction of the main direction x, and the third point as the one that defines the containment on this plane. You can see that this plane has origin in 1.3, 6.7, 2.5, and the c vector, the normal, is pointing in this direction. So I have this situation. I know where this point is in world coordinates, and what I'm trying to do is that I'm trying to find what the coordinates of this point would be in this local reference frame that I have here. All right. I can see visually that x is going to be large, y is going to be probably very short, and z is going to be also fairly large. Okay, just a visual estimation. And then what I have done is I have placed a C# script component and I have created an input called the point that I want to check, another input that is the plane that I also want to that I use as the local reference frame. And what I will generate with this component is a local point, a point in the local coordinates of this plane. Or what I could do is I could just spit out the x, y, z coordinates of this. Actually, let me just do that. We're going to spit out the x, the lowercase x, the lowercase y, and the lowercase z of that point in that reference frame. We need to remember to properly type all the inputs. So I'm going to right click here and I want to make sure that this is of the type point3D, and I want to make sure that the plane is also of the type plane, whatever that is here. All right. And then I'm going to put this in here. I'm going to put this in here, and I'm probably now ready to start doing some calculations. Okay. And you know me already. What I would like to do is I would like to create some function here that I can reuse in other components. And actually, I will reuse this function in a gem that I want to record right after this one. Where what I would like to do is I would create a function that gives me the local coordinates of a point in some other reference frame. So what that means is that that function is going to take as input a point and a plane. So for example, let me call that function local coordinates. And that function is going to take as an input a point 3D called PT. And it's going to take a plane called the coordinate system, for example. All right. And then the return type of this function, what I want to get to know is the XYZ coordinates. However, we know that functions can only return one thing. Well, they can actually return several things if I do refs or if I do outs, but just for the sake of easiness, probably what I want to do is I want to return something that can encapsulate the XYZ properties of these points this point that I'm going to calculate. So probably what I want to do is I want to return either a point 3D object or a vector 3D object, because there I will be able to pack in those X, Y, and Z coordinates that I'm going to calculate. Okay, so and then here in my code, what I would like to do is I would like to say, well, I'm going to create a point 3D object called P, which is going to be the result of calculating these local coordinates from the point that has been given to me in the component and the plane that is given to me as the component. And then here on X, I would like to return P dot the X coordinate. I would like to return here the Y coordinate of that point. And for Z, I would like to spit out the Z coordinate of that point. All right. And if I run this code, it's going to fail because right now my function, this one should be returning something. And because I haven't fulfilled that function yet. So what I'm going to do is I'm going to say returns the point in local returns the point PT in local coordinates of the plane of the coordinate system parameter. All right, cool. Now, what is the next thing that I would like to do? What I would like to do, remember, is I have the plane, okay, and I have the plane, and what I want to do is, let me clean up a little bit of the mess here. Well, I have the plane, I have the point, so what I need to do first of all is I need to create the vector, the position vector, and I need to project that position vector to each one of the three local coordinates, local axes of the plane. So the first thing that I'm going to do is I'm going to create the position vector. So that's going to be vector 3D. It's going to be position vector. It's going to be a vector that goes from the origin of the plane. It goes from the origin of the plane to the point that I want to go. So the way I can do that is by saying, well, I can just take the point, and from that point I can subtract the origin of the coordinate system. So that's going to be coordinate system. Name is very long. I'm just going to do CS here. Okay, coordinate system dot origin. By doing the subtraction of the target point minus the origin point, what I do is I create this one vector that goes from the origin to the target. All right. Now, what I can do is I want to find the length. I want to find the projection of this vector on each one of the axes of the plane. So remember what we just described here. If I do the dot product of that vector with the x-axis, because the x-axis is in unit vector, I will directly get the length of that projection as I have it here in this formula. Because this, for the axis, this b, for each one of the x and the y and the z axis is unit. So therefore, the length of the projection L is just the dot product. All right. So what I can do is I can say, I'm going to create a variable of a double, and that's going to be projection on the x direction. And that projection is going to be the position vector times the x-axis of the plane. So cs dot x-axis. Remember that in Rhino Common, the multiplication symbol stands for the dot product. We could also do this manually, and actually I think I have a function somewhere that we can use for the dot product, but we can also shorthand it. D in Rhino Common means dot product. Okay, and so we can shorthand it with that. Otherwise, if you don't have this in whichever system you're working, if you don't have the multiplication operation between vectors as the dot product, you can compute this yourself. I have a gem somewhere in somewhere. Actually, you know what? Let me go find that out. I'll be right back. Hold on 1 second. And there we go. And so from in Geometry Gem 2, when we discussed the distance from one point to a line, we also discussed all the properties of the dot product. That's where we discussed them before. So if you wanna know more about all this stuff that I have around me, just go to Geometry Gem number 2. Okay. So here we have the dot product. So I could also just say dot product and then one of these and the other one. Okay. Same thing. So I'm going to do that for both the x, the y, and the z. So that's going to be position vector, and this is going to be the y-axis, and this is going to be the z-axis. And then the only thing that I need to do is I just need to return a point with those 3 coordinates. So I can just return a new point 3D with projection x, projection y, and projection z. All right, and I think this should work, right? Let's take a look at that. So I'm going to do this here, okay? And as we estimated, x is large, y is not very large, and z is also kind of large. I wonder if there's any grasshopper plane coordinates. What are the plane coordinates? I wonder if we can double check this. So input point, so that would be this one. S is going to be the local coordinate system. And then here we would have X, Y, and Z. All right. This looks good to me. So the grasshopper, oops, actually my head is in the way. The grasshopper component, both our implementation and the grasshopper component, they both yield the same result. So we're either both right or both wrong. But at least this is looking good so far. Okay. So with that, this is what I would like to do for this gem. What we have discussed, what we have proved is how to take a point that is in world coordinate system and how to project it into a local coordinate system, or in other way, how to find what the XYZ coordinates according to a local coordinate system would be for that point. Okay. Again, this is a super useful operation when you want to do transformations between planes, or when you're doing like computer vision and like you have to work with different reference systems. This is a very common operation to do. Okay. Now, what I would probably like to do in my next gem is show you how, having a point in a local coordinate system, how can I generate that same point in a different coordinate system with the same reference. That's typically an operation that is called a change of basis, and I'm just going to record a geometry gem right now to show you how to do that. So follow me up on the next video. And if you found this useful, if you like what you learned today, just feel free to subscribe, notifications, hit I like, etc., etc. Tell your friends, well, you know, all those things that we do in modern YouTube days. Thanks a lot, and have a good one.